Hello friends, this is Sandeep. So today's our topic is iron carbide equilibrium diagram. So this is one of the important topic in material science which is asked every year in engineering service exam. And if you look at some of the state government jobs exams, you can frequently find the questions asked from this topic iron carbide equilibrium diagram. So generally when you compare with the other subjects questions, so this topic is somewhat very scoring. Why? Because this doesn't require any application of formulas, any remembering of formulas and solving the problems. So this requires only the understanding the concept, what do you mean by iron carbide equilibrium diagram, remembering this concepts and attempting the question. So now let us see what do you mean by this iron carbide equilibrium diagram. So in iron carbide equilibrium diagram, you can study or you can see the different phases. You can study the different phases present in the iron carbon alloy system. You can study the different phases present between iron and carbon. It means you can study the different phases existing in steels and cast irons. So iron carbon diagram equilibrium diagram implies the study of different phases present in steels and cast irons. So generally the phase diagram or equilibrium diagram indicates what are the phases present and what are the properties of phases present at different temperatures and at different compositions. So generally phase diagrams are plotted between temperature and composition, temperature on the y-axis and composition on the x-axis. So let us see in detail what do you mean by iron carbide equilibrium diagram. So it is also called as iron carbon phase diagram. So now let us see how we plot the iron carbon or iron carbide equilibrium diagram. So I will be taking the temperature on the y-axis and composition on the x-axis. So first I am constructing the iron carbide equilibrium diagram. I am taking temperature. I am taking temperature in terms of degree centigrade on y-axis and composition, that is weight percentage of carbon on x-axis. So I will indicate all the different phases present in the steels, that is iron carbon system, in this phase diagram which is plotted in between temperature and composition, that is weight percentage of carbon. So first I am plotting the alpha phase region, alpha solid solution region. So this is the solver's line for alpha solid solution. So I am drawing a horizontal line. So the important point to be remembered is in this iron carbide equilibrium diagram, every horizontal line indicates one isothermal reaction. So in the iron carbide equilibrium diagram, you will be having three horizontal lines. Those three horizontal lines indicates three different isothermal reactions. Those three different isothermal reactions are also called as three invariant reactions. So this is one isothermal, this is one horizontal line where we will be getting an isothermal reaction. This is at a temperature of, this horizontal line is drawn at a temperature of 727 degrees centigrade, and this point corresponds to a temperature of 910 degrees centigrade. Okay, then we'll be going into gamma phase, gamma region. So this is another horizontal line. Which is drawn. So it implies I'm drawing one horizontal line, means at this particular temperature you will be getting another phase change or another phase transformation or another invariant reaction. So this horizontal line is drawn at a temperature of 1147 degrees centigrade. Okay, so this portion implies a solid solution alpha. It is a this portion implies a pure solid solution alpha region. This portion indicates alpha plus gamma. So next I am drawing the region where delta solid solution or delta ferrite exists. So I'm just drawing like this. So this point corresponds to 0.8 percentage of carbon. This point corresponds to 2.03 percentage of carbon. This point corresponds to 4.3 percentage of carbon. I should close one line over here, and this point corresponds to 0.55 percentage of carbon. This point corresponds to 0.1 percentage of carbon. This point corresponds to 0.18 percentage of carbon. And you can observe one more important thing over this is I have drawn a horizontal line over here. So implies there will be one invariant reaction or there will be one phase change occurs at this particular temperature horizontal line. So that line, the temperature at that point is around 1492 degrees centigrade. Okay. So this point corresponds to melting point of pure iron, which is at a temperature 1539 degrees centigrade. So this point corresponds to 1395 degrees centigrade. Okay. So this point corresponds to 1147 degrees centigrade. Fine. So we know that you can say that. What do you mean by this? What do you mean by this vertical line? Vertical line implies 0% of carbon. So what do you mean by that one? It is a pure iron. This vertical line indicates pure iron. This vertical line indicates the composition of 6.67% of carbon. So 6.67% of carbon in pure iron. 6.67% of carbon in pure iron. This is called as a interstitial compound. This is called as a interstitial compound, which is given by the chemical formula Fe3C. It is called as cementite. It is called as cementite, or it is also called as iron carbide. So the percentage of carbon in cementite is how much? 6.67%. Rest all is iron. So rest of how much? 93 point around some 37% is iron. So this vertical line corresponds to cementite, that is 6.67% of carbon. So this vertical line corresponds to 0% carbon. It is called as pure iron. So you know that from room temperature to 910 degrees centigrade, what is the crystal structure of pure iron? That is alpha iron. It is body centered cubic crystal structure. It is BCC crystal structure. So from room temperature to 910 degrees centigrade, from room temperature to 910 degrees centigrade, what is the phase of iron called as alpha iron? Okay, and it is body centered cubic crystal lattice. From 910 degrees centigrade to 1395 degrees centigrade, what they are called? They are called as gamma iron. The phase is called as gamma iron. And what is the crystal structure of the gamma iron? FCC. It is FCC. Okay. Next, again from 1395 degrees centigrade, the crystal structure changes. So it changes again to what type of crystal structure? It is body centered cubic crystal structure. So 1395 degrees centigrade to melting point of iron, that is 1539 degrees centigrade. It is delta iron. So what is the crystal structure of it? Of this body centered cubic crystal structure. Okay. So now what I will do is I will indicate different phases or different solid solutions in this alloy of iron and carbon. Okay. So this phase is called as gamma solid solution. Okay, it is called as austenite. Gamma solid, the pure gamma solid solution is called as austenite. The solid solution of carbon in iron, that is alpha solid solution, that is pure alpha solid solution, or pure ferrite. This is called as the alpha solid solution, and it is represented in this zone. A gamma solid solution is represented in this zone. So what is this zone? In between 1395 to 1590, 39 degrees centigrade, this zone is delta ferrite. Okay. So now I will say maximum solubility of carbon present in this alpha ferrite, gamma austenite, and delta ferrite. Okay. So actually alpha ferrite is an interstitial solid solution of carbon in pure iron. So actually the solubility of carbon in iron at room temperature is very less or negligible, and you can say it has some 0.008 percentage of carbon. At 7, when you heat the iron carbon system, the solubility of carbon in iron increases, and it reaches to a maximum of up to 0.025 percentage of carbon at 727 degrees centigrade. So what is the maximum solubility? What is the maximum solubility of carbon? Maximum solubility of carbon in pure iron, that is in alpha phase, is equal to 0.025 percentage at how much temperature? 727 degrees centigrade. Okay. So maximum solubility of carbon in pure iron, which is called as alpha solid solution, which is called as alpha phase. It is also called as alpha ferrite. So how much it is? It is 0.025 percentage. Okay. So next is gamma solid solution, that is austenite. So the important point to be remembered is gamma solid solution, that is austenite, is an interstitial solid solution of carbon in FCC iron. Okay, and the gamma solid solution is not stable at room temperature. It is stable at temperature above 727 degrees centigrade. Okay, you can see here above 727 degrees centigrade only the gamma phase exists. Okay, so it is not stable. It is not stable at room temperature. From 727 degrees centigrade, upon heating, the alpha phase changes to gamma phase. So the minimum temperature at which gamma solid solution formed is 727 degrees centigrade. That is one of the important question which is asked many times. Okay, so you can see from this picture. So as the temperature increases, the percentage of carbon dissolved in gamma iron increases, and it reaches maximum of up to how much? 2.03 percentage. Okay, so what is the maximum solubility? Maximum solubility of carbon in FCC iron. Means at higher temperatures, the body centered cubic crystal structure of iron converts to face centered cubic crystal structure. So FCC iron means it is gamma austenite. The solid solution is gamma austenite. How much it is? It is equal to 2.03 percentage. It is equal to 2.03 percentage. At what temperatures can you say? It is at a temperature of 1147 degrees centigrade. At 1147 degrees centigrade. Okay. Similarly, what is the another solid solution what is the another pure solid solution you can observe? It is delta ferrite. Okay. So in delta ferrite, the maximum solubility of carbon is 0.1 percentage. Okay. So in delta ferrite, what is the maximum solubility of carbon? It is equal to 0.1 percentage carbon. Okay. So I think you are clear with this. Okay. The maximum solubility of carbon in alpha phase, in alpha solid solution or in alpha ferrite is 0.025 degrees, 0.025 percentage. The maximum solubility of carbon in gamma phase is 2.03. The maximum solubility of carbon in delta ferrite is how much? 0.1 percentage. Okay. Next in this iron carbide equilibrium diagram, we will see the three different invariant reactions which are taking place. Okay. So let us see those three different invariant reactions which are occurring. Okay. So first of all, I will start with this horizontal line. First of all, I will start with this horizontal line where peritectic reaction takes place. Okay. So at 1492 degrees centigrade, what is the invariant reaction which is occurring? Peritectic reaction. So what I will do is I will just magnify this part of the image and I will draw over here. Okay. So what are the things over here? So this is one horizontal line. Okay. So I'll just erase something. Okay. So this is one line. This is one line. Okay. Next, what is the other thing? This is the other thing. Okay. Next, this is the another curve which is seen. Okay, fine. So this is the delta. This is delta ferrite. Okay. So I have not marked what are the phases existing over here. Okay. So this is pure liquid. This is liquid. So all the phase over here is above 1539 degrees centigrade. That is melting point of iron. All the phase over here is liquid. Okay, fine. So this portion. Okay. So this portion is liquid plus delta. This portion is liquid plus delta, and this portion is delta plus gamma. Okay. This portion is liquid plus delta. This portion is delta plus gamma. Okay. I'll say clearly about these phases over here. Okay. So this is completely liquid. Okay. This is liquid plus delta. This is delta plus gamma. Okay. So let us to avoid the confusion name the points on these lines. Okay. So let us say this point is A, this point is B. Okay. Let us say this point is somewhat C. Let us say this point is somewhat D. Let us say this is let us say this is E. Okay. So as I mentioned over here, this point corresponds to how much percentage of carbon? 0.1 percentage of carbon. Fine. So this point corresponds to how much percentage of carbon? 0.18 percentage of carbon. Okay. So in the iron carbon equilibrium diagram, every horizontal line indicates one invariant reaction. So this is one horizontal reaction. So the point to say to you is at this point D, peritectic reaction takes place. Okay. Means at that point D, under equilibrium cooling, phase change occurs. Okay. So what is the peritectic reaction is liquid. Okay. Liquid plus delta upon cooling. Okay. This is heating. Liquid plus delta upon equilibrium cooling, it transforms to gamma. Okay. So the portion over here is gamma. Okay. So liquid plus delta gives rise to gamma. It occurs at how much percentage of carbon? At 0.18 percentage of carbon. It means that it is at point D. So can you say what is the percentage of carbon in liquid? What is the percentage of carbon in liquid? So this is what is this line? This line is liquidous line. This line is liquidous line. Fine. So what is the percentage of carbon over here? What is the percentage of carbon over here? You want to know the percentage of carbon in liquid phase. So what you will be doing? You will be concentrating on this point. You will be drawing a tie line, that is a horizontal line, you'll be meeting that tie line or horizontal line up to liquidus line, and you'll be dropping on x-axis. You'll be dropping this point on x-axis, that is on composition. So at point T, what is the percentage of carbon mentioned? It is 0.55 percentage of carbon. So in this liquid, how much percentage of carbon is there? 0.55 percentage of carbon. Fine. Next, at this point, peritectic reaction is taking place. So delta. So delta, in delta, how much percentage of carbon is there? You take this point, move to the left. That is, you are taking a tie line. You are touching the delta line. And you draw the vertical line. So it corresponds to how much percentage of carbon? 0.1. So liquid plus delta at 0.1 percentage of carbon transforms to gamma. So in gamma, at this point under equilibrium cooling, liquid plus delta is transforming to gamma. So here upon equilibrium cooling, upon decreasing the temperature, you are getting gamma solid solution. So what is the percentage of carbon present in gamma? It is equal to how much? 0.18 percentage carbon. So it is 0.18 percentage carbon. Okay. So this is the peritectic reaction which is taking place. So liquid plus delta transforms to gamma. Okay. So this is how one invariant reaction takes place. So why this is called as invariant reaction? So invariant reaction means degrees of freedom is 0. Okay. So at this point you are getting phase change of liquid plus delta transform to gamma. Okay. So it occurs at a particular composition and at a particular temperature. Okay. It occurs at a particular composition of 0.18 percentage carbon, and it occurs at a temperature of how much? At 1492 degrees centigrade. Okay. At 1492 degrees centigrade, peritectic reaction takes place. Okay. So that's why it is called as a invariant reaction, where the degree of freedom is 0. It occurs at a particular composition and at a particular temperature. Those values are fixed. Okay. So this is one invariant reaction which is called as peritectic reaction. We will see the next phase change which is occurring in this iron carbon equilibrium diagram, or we will be seeing the next invariant reaction which is occurring. Okay. So the next invariant reaction occurs at, let us say this point is E. Okay. So at point T, at 4.3 percentage of carbon, you will be getting eutectic reaction. Okay. You will be getting eutectic reaction. Okay. So what is eutectic reaction? What is eutectic reaction? Liquid upon cooling, liquid upon equilibrium cooling. Okay. Or I am taking the reverse as heating. Liquid upon equilibrium cooling, it transforms to two solids. Those are gamma plus Fe3C, that is cementite. Okay. So this portion is gamma plus Fe3C. So what is the percentage of carbon in this liquid? It occurs at a carbon percentage of 4.3. Okay. So this is 4.3 percentage carbon. Next, what is the percentage of carbon in gamma solid solution or austenite occurring at this point? So you just draw a horizontal line. You just draw a horizontal tie line. It is intersecting the gamma line. So what is the percentage of carbon in it? 2.03 percentage carbon. So how much percentage of carbon it is? 2.3 percentage of carbon. Okay. Now at this point, what is the other phase which is forming? Cementite. What is the percentage of carbon in it? You just draw a horizontal line to the right of it and drop the vertical. What is the percentage of carbon? 6.67. So it is 6.67 percentage carbon. Okay. So this invariant reaction is called as eutectic reaction, where liquid transforms to gamma plus Fe3C. So this mixture this mixture of austenite plus cementite is called as ledeburite. Okay, this mixture of austenite plus cementite is called as ledeburite. Okay, so these are the solid phases which are existing, or these are the solid phases which are forming. Okay, but you cannot see these solid phases. You cannot see these solid phases in the microstructure, or you cannot from the microstructure you cannot see these solid phases. Why? Because gamma solid solution or austenite doesn't exist at room temperature. Okay, this reaction occurs at a temperature of 1130 degrees centigrade. Okay, sorry, this reaction occurs at a temperature of 1147 degrees centigrade. Okay, this eutectic reaction occurs at a temperature of 1147 degrees centigrade. You cannot see the microstructure, or you cannot see these solid phases. What are those solid phases? Austenite and cementite in the microstructure. Why? Because austenite is not stable at room temperature. Okay, austenite transforms to two more phases. Okay, austenite transforms to ferrite and cementite, that is perlite. Okay, so we will be seeing the the third type of invariant reaction which is occurring in this iron carbide equilibrium diagram. Okay, so that third type of the invariant reaction which is occurring in this iron carbide equilibrium diagram is, third one is Eutectoid reaction. Third one is Eutectoid reaction. So Eutectoid reaction occurs at a percentage of carbon of 0.8. Okay, so what is this Eutectoid reaction is? So what is this Eutectoid reaction is? Gamma transforms to upon equilibrium cooling or slow cooling, the gamma solid solution transforms to mixture of two solids. Okay, mixture of two solids, those are called as alpha plus Fe3C. Okay, mixture of two solids. What is alpha? Alpha is a solid solution of carbon in iron. Fe3C is a interstitial compound. It is called as cementite. Okay, so Eutectoid reaction occurs at a temperature of 727 degrees centigrade. Okay, so what is the Eutectoid reaction? Gamma solid solution upon cooling. Okay, the reverse I am taking as heating. Gamma solid solution transforms to alpha plus Fe3C. Now can you say what are the percentage of carbon in these solid solutions or in these phases? Gamma phase, alpha phase, and cementite. Okay, so in gamma phase, what is the percentage of carbon present? 0.8. Okay, 0.8 percentage of carbon. Okay, in alpha phase, you just at this point where the Eutectoid reaction is taking place, you just draw a horizontal line. Okay, you got the alpha line, you got the alpha solid solution area, you just drop a vertical. Okay, you just drop a vertical, you can find the percentage of carbon at this point. Okay, how much it is? 0.025. Okay, so this alpha is 0.025. Okay, similarly you draw the tie line. This is the tie line which I drawn. You project it to the right side. And drop the vertical. What is the percentage of carbon? 6.67. So what is the percentage of carbon here? 6.67 percentage of carbon. Okay, this is 0.025 percentage of carbon. Okay, so what is the Eutectoid reaction which is occurring at a 727 degrees centigrade? Gamma transforms to alpha plus Fe3C. Okay, so this mixture of two phases which are called as alpha and Fe3C, this is called as perlite. Okay, so perlite means it is not a phase, it is a mixture of two phases, alpha and cementite. Okay, perlite is a mixture of ferrite, alpha ferrite mixture of alpha ferrite plus cementite. Perlite is a mixture of alpha ferrite and cementite. Okay. So this is the eutectoid reaction occurring. Okay. So in the perlite, okay, the shape of the microstructure of the perlite looks like fingerprint microstructure. It is called as plate-like microstructure or lamellar in shape. Okay. So those all things, how the microstructure of perlite looks will be drawing when we discuss the how the microstructure changes occurs during the equilibrium cooling. Okay. So when you take a particular percentage of carbon, if you do equilibrium cooling from high temperatures to low temperatures, okay, you can draw the microstructure. Okay. So how the microstructure of perlite looks, okay, all those things we will be knowing when we discuss the equilibrium cooling of any particular alloy. Okay. So this is about the eutectoid reaction. Okay. So generally the steel is used for most of the applications. Okay. After the concrete, the steel is widely used material. Okay. So why the steel is widely used for many applications is because if you look at this perlite phase, okay, perlite is a mixture of ferrite and cementite. Okay. So ferrite is very soft. Why ferrite is very soft? If you, the pure iron is very soft and ductile. Okay. So alpha ferrite is having a small percentage of carbon dissolved in pure iron. Okay. So alpha ferrite is very soft. Okay. And cementite is having 6.67% of carbon. Okay. And it has complex orthorhombic crystal structure. Okay. So this is a very hard and brittle phase. Okay. This is a very hard and brittle phase. Okay. So you are having a combination of both soft phase and hard phase. Okay. So that's why the steel has been used for many applications. Okay. So by varying different percentages of ferrite. Okay. By varying different percentages of ferrite and different percentages of cementite. Okay. By varying different percentages of ferrite present in the steel and by varying different percentages of cementite present in the steel, still we get further many mechanical properties for the steel. Okay. So that's all for today. So we have discussed about 3 different invariant reactions which is occurring in this